Hi, welcome back to the video of numerical differentiation. I think if you already watched the previous one, I already introduced about the steps that we need to do the numerical differentiation. Okay, I will have a summary about what are these steps. The first step is we need to generate the x-axis, and the second step we need to generate our function, the array representing our function, and the final step is to find the derivative based on the generated array of function. And in this video I will go deeper in the detail of each step. So for the first step we need to generate the x-axis. So this is the code as you already see. First, we need to import the necessary library, which is the NumPy, and this is a very important one to generate the x-axis. First, we need to specify how many discrete points that we want to use in order to represent our x-axis. In this case, I just want 10 points. Here the array containing only 10 points, and then I will put it in this numpy linspace. What does this mean? 0 or 9? The 0 means I want the first value starting from 0. The x0 is 0, and then the last value in the x-axis array will have the value 9. So here is 9, and I want to generate 10 number of points, 10 values in this array. This one means I want the function to generate the 10 points in this range from 0 to 9, and also when it generates, it will compute the step size h and return back for me. So as a result, the x here, I also printed here. The x returned by the NumPy linspace containing two parts. The first part is the x-axis representing numerically, and the second part is the step size h. So next is we need to extract the step size h from the x, and because it has the x, this is the whole x, and the first element is the x-axis values, and the second element is the step size. The index is 0 for the first element, and the index is 1 for the second element, and with that one we can got the step size. Finally, we will extract the x array, which is very important here. So I extract the x-axis array from the x variable at the index 0, as I said. These two common lines equal to what I'm doing here. They are totally equal. It just, instead of I'm using the x-axis variable to store the first element of x, you could use the x itself to store only this variable. So yeah, with this code you can have this array containing 10 discrete numbers. Each number represents a value along the x-axis. Based on what, we will compute our function array to representing the blue curve, or representing an arbitrary function. And this is the step number 2, generate the function fx based on the x-axis computed by the step number 1. Because I just illustrate a very random blue curve, so it's very hard to know what is the exact function of this blue curve. That's why I choose a better, easier, more familiar function, which is x squared. I will generate the function of x squared. And in order to generate the function, of course, we need to define our function. And this is how we define our function. The name of the function, the independent variable, and return the form of the function based on the independent variable. And because I want to generate the x squared, that's why I just need to return x squared here. And after that, we need to use our function to generate the array containing the function value. And here we use the define f function, and we input the x-axis. We input the x-axis in order to have the array representing the function. So now the function x is the array containing all of the points representing our function. And you could see this is our function. This is our function with representing by the array fun x. This point had this value. At this point it has this value, and etc. At the end point it has the end value. More specifically, as you could see, I also print out the value of our function, because when x-axis has 0 value, if you remember in the first step, we have the x-axis with the value of 0, 1, 2, 3, 4, etc. until 9. Now, when we want to generate the x square, so at 0 we have 0, at 1 we have 1, at 2 square is 4, at 3 square is 9, and at the end point 9 square is 81. So we have very cool function. Finally, we need to compute the derivative of our function in step 3. I'm using the forward differentiation. This is the formula to generate the forward difference. And this is the code. Here I just want to summarize again the function. This is our function, the array representing our function. Okay, and the first element is the value at x equal to 0, which is 0. Next is the value at x equal to x1, so it has 1, and go on until the final point we have 81. Okay, and this is only the conversion. Okay, this is how we understand the value, but as a computer can understand this one. Fx at the index 0 equal to this value. The value fx1 equal to fx at the index 1, and so on. So this is how we understand the value, but here is how the computer understands the value. So with this formula, with this understanding of the array representing our function, we can derive the derivative. So let's say we want to derive the derivative at x0, derivative of fx at x0. We need to have 1 point forward, right? This is the forward point minus our point divided by our step signs. So here we have the x-axis, the value x1, of course, equal to x0 plus the step signs. So we can do the conversion from x0 plus 8 is equal to x1 here. So these are equivalent. And as I already say also, fx1 is the way as a human understand, but the computer understand is the fx variable at the index 1. So in order to convert from human language into computer language, we have this one here. fx1 is the fx at index 1. fx0 is the variable fx representing the array of a function at the index 0 over the difference of them over the step signs. Similarly, if we want to compute the first derivative of the fx at x1, we translate from human language to computer language. This one is how human understand, but we translate into computer understand is the fx at the index 2 minus the fx at the index 1. We have the difference over age, step size, and then move on to all of the points. We will have the general formula in order to input as a computer language into the computer. If we want to generate the derivative, the first derivative of the function at x equal to xi, we will have the fx variable index x at y at I plus 1 minus fx function index as I with the difference over the step size h. So based on this general formula, general language for the computer, we can write down our code. So you can see this is the formula and this is the formula. I put it here because we need to repeat this formula many points along each point of the x-axis, and n representing the number of points along the x-axis. 0 is the starting point, I is the index, and each time we generate the value of the differentiation, we need to store it into somewhere. We will store it into this variable dfx. So dfx is where we need to store our value. So this is everything. So let's run the code and see. The code is here. Yeah. So the first step is generate the x-axis. Okay, let's run the code. I run the code in Google Colab. Okay, now we got the generated x-axis from 0 to 9 with the step size of 1. Then we generate our function at the second step. We define the function and then we generate the function. We print out the value of our function here. If you want to illustrate, also you can plot the function. So this is our x-axis. You could see from 0 to 9. And our function from 0 to 81 with the shape of x square shape. So totally correct. Now let's compute the differentiate of our function, the first order differentiation of our function. We use the general formula and also store the derivative of each point into somewhere in order to have the whole differentiate of the function, the first order differentiate function of our function. So dfx representing the derivative function of our function. So let's plot our function and also its derivative. So here the first figure is our fx, our function, but the second figure is our first derivative function of our fx. So dfx, second is dfx. You could see if we have a curve, the derivative of a curve like this will be a straight line going up. Exactly right. So this is the end of numerical differentiation. I hope that is useful for you. If you have any comment about my content that is not clear, then please give me some comments. I will put also the code inside the comment section of the video. See you.